Hello students, welcome back. There's still one more issue left from section 1 of this notebook. Let's take care of that before moving on to the next section. Previously, we studied only this type of example. The first-order linear system written in the standard form. Standard form, what do you mean by that? We have only one derivative each line. y1 prime equals to something. y2 prime equals to something, and so on. We have yn prime equals to something, and no derivative here, just one derivative each line. That's the standard form. And then, based upon the standard form, we develop the matrix expression, simplified further, and then finally, we can define the linear operator based upon those, so that we can apply the theory of linear operators as we did in chapter 4, and that resulted into this and that. I'm not really a fan of principle of superposition, but this one's really important. How do you get the solution, the general solution of a non-homogeneous system? Just by adding up the general solution of the homogeneous system plus a particular solution. That's really important, and that's why homogeneous system is really important. We study those, and then particular solution parts separately. But then again, what if we have far more complicated system like this? Previously, we had only the standard form. We have only one derivative. Here, I have many derivatives in each line. So this system here is far more complicated than this one, especially in terms of the derivative part. We have only one here on the left-hand side, but here I have too many. And then the matrix expression does not look too bad, but you're going to get something like this. This part here, where my mouse is running around, that's by prime part. And the second part here, that's cy part. And then equal to g like this. Of course, I use different characters to avoid confusion. Now, what if we started from something like this? Can we still do the same thing and define the linear operators and develop the same theory? The answer is yes, and the method is theoretically possible, but it's going to be tedious. Basically, what we do is from this system, consider this system as a system of n algebraic equations of y1 prime through yn prime, and solve those algebraically with respect to the other terms. Other terms I mean by y1 through yn and g. And then if you do those, then, well, in the end, you can solve for y1 prime, y2 prime, y3 prime, and so on. So in the right-hand side, we have a certain linear expression, and we can name those as the standard form like this. Basically, what we are doing is this kind of matrix computation. So from here, and then flip the cy to the other side, like this, and then divide by b. What do you mean by dividing by b? It's matrix. So we have to multiply its inverse matrix. Multiply by b inverse, then let's see, from here. Okay, let's start from here. We get that, and then from here I can multiply by b inverse. And multiply by b inverse. By the distributive property, I can multiply by inverse to each term like this. And then these two cancel each other out, because this is nothing more than an identity matrix. So we just have y prime. And then the right-hand side, I'm going to name this one as A, and that one as F, and then my transformation is complete. What we have here is the standard form, this one. So even if I start from the general form like this, far more complicated, and then if you compare this one with the standard form like this one is far more complicated because we have too many derivatives here intertwined. But with some tedious algebra, tedious but elementary, we can solve for y1 prime to yn prime and then get the standard form, and we can go from there. So all the theory of linear operators and so on, they can apply. Now, if you have a problem like this, then maybe you have to do some extra algebra to convert into standard form, and maybe you can start from there. And that's going to require some work, but nothing really fancy. Tedious, yes, but they're elementary. Now, one final question here. When you divide by b, in other words, multiplying by inverse, is it possible? Because not all square matrices have inverse. What if b inverse does not exist? In that case, as a matter of fact, it turns out you won't have to worry about those. What do you mean by those? That means, these by part, all these, those are not all linearly independent, and some of them are redundant. So basically, even if you started with, say, 7 equations, because of the redundancy or maybe conflict, we are coming down to 5 equations, for instance. So we end up with 7 unknowns and 5 equations. Hey, that's impossible. So we don't really have to bother with it anyway. So if B inverse doesn't exist, then it's impossible to solve that system anyway, so you don't really have to bother. So the conclusion, in theory, it's okay to start from the standard problem. And in general, if you have some general form, then you can always convert it into the standard form and you can go from there. Alright, that was the final topic that I wanted to add to section 1. And the section 2 begins in a separate video. Let's stop here.